Guys, welcome back to the channel. Let's solve another challenge. Today's challenge is problem from a LeetCode, walls and gates. So let's see what we are given. So we are given an m by n grid rooms initialized with these three possible values. Basically, -1, it's a wall or an obstacle. And this if -0, number 0, it's a gate, or infinity means empty room. And we use the value 2 power 31 minus 1 is this big value to represent infinity, as you may assume that the distance to a gate is less than this. So now we need to fill each room with a distance to its nearest gate. If it's impossible to reach a gate, the rooms should be filled with infinity, right? Basically, this is example 1. You can see there are two gates and empty rooms, so we need to fill each room with a distance to its nearest gate, and that's a return, right? So before we just discuss this example, let's see what are the constraints. So the constraints are m is the room length, and width is n, and m and n, it can range from 1 to 250, and each room value can have -1, it can have 0, or it can have 2 power 31 minus 1, which is the infinity. So let's see this problem in the whiteboard. So this is the same example. Right now, how many rooms we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We have 9 rooms. Basically, these are empty rooms, right? And these guys are walls. How many walls we have? 1, 2, 3, 4, 5 walls, right? And how many gates we have? We have here it's 1 gate, right? And we have 2 gates. So these empty rooms, they have a specific distance to the gate. So we need to return the shortest possible distance to the gate. For example, from this room to the gate 1, and this is a gate 2 to the gate 1 distance, and 2 distance, 3 and 4. Up to this gate we have a distance 4. Up to this gate we have 1 and 2 and 3. So we have two options. Either we can say it's 4 to the first gate, and to the second gate it's 3, right? So we need to just get the shortest distance. And these values, how we can calculate, right? We have this side is the number of rows, and this side is number of rows, and this side is number of columns, right? Columns. And we cannot move through this obstacle, right? These are the walls. We cannot really cross these walls. Initially, the distance to each gate from each room is infinity. We just say this is infinity sign, right? Infinity sign. How we can start, right? Can we start from each room and see the distance to each gate? Is that the clever way? In that case, we will have to do many repetitive redundant computation, right? For each one, we need to just go up to this gate. We need to search for all the possible gates, right? And just try to update what is the minimum one, right? And we need to be repeating for each one, right? For each room, we have to be finding the minimum distance, right? the shortest distance for each. And from this, we need to go all the way here, and we need to go all the way to search for another gate if there is any possible, right? Possible gates. So this is the one way, right? For this one, there is only one. For this one, we can go 1, 2, and 3, or 1 to the first gate, 1, 2, 3, 4, 5, and 6. And for this one, then we are going to update the minimum one, right? That way, it's very inefficient because for each room, we have to be searching for entire grid if there is any potential gates, right? And compute the minimum or the shortest distance. This is one way. And another way is instead of starting from a room, we can start from the gate, right? Let's see what we can do if we start from a gate. Initially, each distance we just fill with infinity because this is how it's given, right? So everything is infinity. Now let's start from a gate. From the first gate, we can start this gate 1 and gate 2. Each one of them, we say we add this each gate because that's the room. These gates are filled with 0. They are in the grid. Their label is 0, right? Then each room they are labeled as infinity, and each of these walls they are labeled as -1. So we need to make sure that we cannot cross these walls. Now we can do this DFS traversal of this entire grid, or we can do the BFS traversal of the entire grid. But how can we do the BFS? So BFS is more effective, and it computes the shortest distance layer by layer. Let me show what I mean to do this layer by layer. Let's say for each distance, we say, let's say the distance from a gate to itself is 0, right? Because that's the distance from each gate to itself is 0. Now, then what we do, we add each gate to the queue. Then we start processing the next layer from each gate. See, here what we do, we try to search if there is any room from each gate, right? We go to the up, down, and left and right. Left, we cannot go because there is a wall, and the right. And we see this distance, that's like 1. The next one, we can also go from this gate to down. This is 1. From this gate, it's also 1. So which means for this specific, let's say, layer, so we say, okay, this is the first layer, and we compute the distance. This is like first layer. Then this 3 values, this cells, right? These 3 cells at the first layer, this one, and this one, and this one, they are going to be the first layer. So that's how we traverse, right? So then we add these 3 layers, 3 cells to the queue. Then from here, we start processing the next potential cells. Let's see, from this, which directions we can go? Can we go this way? No, we cannot go because there is a wall. We can only go the next layer here. We compute 2. From here, which way we can go? From this cell, right? This cell, we cannot go up. We cannot go this way. We cannot go, right? Because there is it's a gate. And this way we cannot go. Basically, for this cell, we are done. We are done processing all the neighbors, right? And let's see for this cell where we can go. We can go here. Initially, the distance up to here is 1. What about here? We need to add this distance 1, so it will be distance 2. And if we go down, can we go to the right? No, we cannot go. But we can go to the down. Can we go to up? No, we cannot go because that we need to check if that's empty room, right? So we see that this is also empty room. We can go this way, right? From from 1. So then we are going to update the distance, right? Now this 2 is going to be next layer, right? Next layer, we are going to mark this as the layer number 2, right? Okay. Well, right now these ones we add to the queue to process next, right? This 3, and for each one of them, we start processing if we can move to any empty room. Let's say start from this. Can we move to any empty room? No, because this one is already we computed distance. It's not empty anymore. This way it's not empty anymore. This way there is a wall. This way there is a wall. We cannot move. What about from here? From here we can move right, and we cannot move to the left. We cannot move down. We cannot also move to the right because it's not empty. We can only move to an empty room. So we can move to the empty room, and it is distance up to here is already 2. We add 1, so it will be 3. And from here we cannot go anywhere else except down, and we compute 3. So this will be the layer 3 of in the queue. Let's see, mark them as it was a different color. So then from here, can we go anywhere? No, we cannot go anywhere. All sides are blocked, right? We are done with this one, right? We can pop it from the queue, but we cannot really process. And here, can we go to the left? No, up is occupied and down is the boundary, right? And we can only move to the right, and we just add 1 to this one, right? And it will be the layer number 4. And let's see the different colors. So it will be layer number 4. So right now you can see initially we are done visiting and computing all the distances, all the shortest distances potential towards the gate, right? Let's say that initially we have this 2 and this one as a first layer and distance 1. After that we computed this distance 2. After that we computed this distance 3, and finally we computed this distance 4, right? Then once we last element 4, that will be added to the queue in the BFS, and we also pop that and see if we can move to any empty room from this 4, and we see we cannot really move to anywhere. So that's the end. That's where we stop. So this problem has 2 steps. The step 1, we find all the gates. I come back again. We find all the gates. Gates are labeled as 0, right? Gates are labeled as 0. We find all the gates. We add that to the queue, and we pop and see its next potential cells, right? That we can move, potential rooms. Then the step number 2 is basically we form BFS, right? To update the distance to the neighboring cells. And let's see this in the code, and I will try to write the code from scratch, and maybe the things will be clear in the code too. Okay, let's see. So if there is no room, then we return nothing. And all the gates are in the grid. They are labeled as 0. They are filled with 0. All the empty rooms are labeled with this in the grid, which means it's infinity, right? We don't really know the distance to the nearest gate. And from we are given this rooms grid, and we get the rows and columns of the grid, right? The rows and columns, that's how we get. Then after that, we define the direction to move in the grid from the specific cell, right? We can either go to up, down, and right and left, right? So after that, we need to initialize the queue, right? To add the gates, right? So let's initialize the queue. We initialize the queue as as dq. Then for we're gonna check in the entire grid if any of the grid cells we can they are all the gates we need to add, right? Basically for row in range for row in range rows, right? And for columns in range calls, because that's these are the columns. Then now we check if rooms row and specific column is equal to 0, which means that's a gate. Then we add those gates into the queue, right? That how we define was defined by the row and column of that specific gate. So basically, this is that's how we add the gates to the queue, right? Now we start processing. Now we start processing the queue while queue is not empty. Then we get the size of the queue with len queue, right? With a len queue. Then for each layer, now we need to just go for each layer in the grid, right? Let's say in the distance 1, right? All the neighbors of the gate, which are the potential neighbors, possible neighbors of the gate. For we don't need to go through this in size, no, in range size, right? And we need to pop from that row and column those gates. The thing that we pop, they are the gates from the queue. So after we pop here row and specific column, now we need to explore from that from the gate, right? Initially it was the gate in the queue. From that gate we need to explore all 4 directions. We need to go up, down, left, and right, right? Because that's those direction. That's how we specify it here, right? And for each direction we compute the new row and new column, right? For the next layer in the grid. The new row is old row plus the dx, and the new column is old column plus dy. And we need to make sure that the new row or new column, a new cell basically, they are within the boundary of the grid. If the new row is between 0 and the rows, number of rows, and if the new column is between 0 and number of columns. And we need to make sure that rooms at the specific calculated new row and new column, that room is empty room, and that's empty room. That's how we define, right? Empty room is equal to this, which means like it's infinity, right? If that's empty room, then for the distance of the new room and new row and new column cells, we need to add the distance from the previous here, right? Previous cell, old cell. If we are here, the next one we compute this to compute the distance to this one, and this is an old one plus 1, right? That's how we are computing the distance. That's what we are adding when we compute the new row and the new column. So we need to add the distance from the previous one, right? And yeah, that's how we are adding this. Then after that, after we update the distance, then we need to add that cell to the queue and go back, and until we need to traverse entire grid and update their distances, each distance from each cell to the nearest gate. With the distance, and this queue will be empty after we are done processing all the cells, all the rooms, right? All the cells within the grid. So time complexity is O of number of rows times number of columns, and the space complexity of this approach is also number of rows times number of columns, right? So yeah, this is it for this problem. So this is a very interesting challenge from LeetCode 286, walls and gates. So here to recap, so we have two steps. The first, instead of starting from all the empty rooms, we are going to start from a gate processing, add them to the queue, right? Identify their value. If it's 0, then add them to the queue. From there, we try to search using the BFS. It's called, instead of using this from one gate, we are going to start using from both gates. It's called multi-source BFS, right? With the queue, and that's how we update. Once each distance is updated, so it's not empty anymore. So that's the shortest distance. Like, we only update the distance if the room is empty, right? So that's it for this problem. And if you like this whiteboard approach and live coding, please share your thoughts and comments. And if you would like to see more videos, yeah, please let me know. Thank you.